All right, so my name is Samuel Antao and I come from IBM Research, and today I'd like to tell you a little bit about the work that we have been doing about adding support for OpenMP offloading for GPUs in a Clang compiler. So I go directly to the first slide here, when I try to summarize some of the properties of OpenMP. So OpenMP is about a directive language that allows the programmer to annotate the code and control the execution in parallel of different sections in the code. So you can assign a given directive to a given code region to specify I want the iterations on this loop to be distributed by a lot of threads. I also can specify tasks along with a set of dependencies, so I can execute these tasks in parallel and still force the execution to comply with these dependencies. And also, it can be used to give the compiler hints about optimizations, like we have loops that we can try to make symmetrization and things like that. And another thing that is nice about OpenMP is that it has a specification both for C, C++, and Fortran. So one thing that is new in the latest specification in 4.0 is the ability not only to take advantage of the host resources, but also of targets and or accelerators that may be attached to your system. So we now have directives to specify offloading of a given structure block into a given accelerator in my system. So I can mark these target regions. I can try to specify how I'm going to do the data movements. And one thing that is true for these target regions is that any directive that is valid for the host can be also present inside these regions. And one of the challenges that this poses to someone that is trying to implement a compiler for this is that the code generation for a different target. All right. So the challenge is that now we have in the same system, and we need to make the same compiler to support like a huge range of different targets, with the challenge of the code generation for each one of these targets is potentially different. So that means that if we have very good approach for one target, that approach may not be very good for other targets, and this is a challenge for the compiler. All right, so in this slide here, I try to illustrate a little bit how does an OpenMP implementation looks like. So here we have the OpenMP enabled compiler. So you need something that is able to understand whatever directives I have in my program. And this compiler is going to produce a fat binary that now not only is going to contain the host code, but also the code for the devices I want to use to accelerate my execution. And these two pieces in this fat binary are going to interface with runtime libraries. So we have a runtime library for the device, and we also need a runtime library for the host. And the latter we can divide into two subcomponents. One is to deal with operating system, like request threads from the operating system and try to distribute the workload to these threads. And another component is required to deal with the target, to deal with the offloading to the accelerator. And in implementation that we are doing, this component has like two subcomponents. One that is target agnostic, and this is all about maintaining the state to maintain like a record of the maps between what a pointer means in a host and what a pointer means in a device, and maintain this state. And another component that is target dependent that the runtime uses to speak with the driver, so I can offload, launch the execution on the device, or I can move the data to the device. And so for the work that we are interested in doing now, we are using a given system, and that is based on a Power 8 and NVIDIA GPUs. And so in order to support these GPUs, we are using the CUDA runtime library to support the host part of the target offloading. And what you are interested is having Clang as a compiler for OpenMP. So this is exactly about this component that I'm going to talk a little bit more in this talk. Just a side note, I'm not currently dealing with Fortran, so Clang is only a C compiler. I'm not going to talk about Fortran in this talk. So, all right. So, I don't know how many of you already know what LLVM is. I'm just describing you very, very quickly what LLVM is about. So you can see LLVM so it's an open source infrastructure, and you can see it as a library that one can use to build compilers. So it has a very strong API that allows you to interface with this library. Has a very modern code base. You should expect to find in this library state-of-art algorithms that you can find in any other compiler, production quality compiler. And one thing that is very important for the work that we have been doing is that we already have support for some backends, namely the PowerPC and the CUDA-enabled GPUs through the PTX backend that LLVM has already in place. Another property of LLVM is it has a very well-specified intermediate representation that makes very easy to interface with. So right now you can find a lot of different projects orbiting around LLVM, and one of the projects that we really care about for this is Clang. So Clang is nothing more than an LLVM IR client for the C family programming languages. And what is good about Clang is a very fast development pace. You should expect to have the latest developments in a given specification of a language to be already implemented. And also, nothing of Clang is that it not only acts as a front end, but as also components to drive this library and call all these different components, so I can have front end, optimizer, back end, everything driven by Clang. So one thing that is common about these two things is that they have a very modular code base, so which allows the developer to more easily add new features and improve the maintainability of the code base. Another nice thing is the license. So if you are interested in having in creating and create a new compiler, and you want to provide your customers this compiler, you are able to do that. The license allows you to do that. In what concerns OpenMP, the support for OpenMP 3.0 is already in place, and but this has been done as an external project of Clang compiler. So what happened? There was a snapshot that was taken from the main repository, and the OpenMP development is being done on top of this. I'll get into more details about where you can find this OpenMP implementation in the last slides of this presentation. All right, so what Clang has to do in order to support offloading? So in this picture, I'm just showing you the how the compiler toolchain looks like, and what is new when you have to support offloading is that you not only have to support host toolchains like with the processor, compiler, and assembler, but you also have to support like some different toolchains by the same compiler. So all this thing is already in place in Clang and implemented. So what happens is that for each input source, I use the host preprocessor to obtain the preprocessed source code, and then I'm going to feed this preprocessed file into many toolchains as many targets the user specified. So I'm going to use these toolchains to obtain the host object, and this toolchain to obtain the target objects. So then I have a phase that is going to link all the target objects inside a shared library. So, I mean, I would say a self-contained image in the sense that there are any symbols left to be defined, and then the host linker is going to link the host code as well as integrate the target image as is in a given elf section, so in a given section in my object, so that the runtime knows where to locate the image code and be able also to offload this code to the device by moving the bit stream to the device. So this is what Clang is doing as a driver when I want to support offloading. All right, so other component is the code generation. And in order to understand code generation, we also need to understand the constraints of the target we care about, which in this case is the GPU. And there are very, very unique properties of GPUs that we need to bear in mind. One is that it has massive amount of threads that are executed in wavefronts that are called in CUDA Warps. We have threads divided into a logical abstraction that groups the threads in sets that and they are assumed to collaborate more closely. And yep. So the question is, what's the difference between a warp and a block? So a warp, you can see it as the unit that is used to schedule the execution on a GPU. So there is the amount of threads that are executed simultaneously at a given time in a GPU. So a block consists of several threads that are grouped in warps. And what is going to happen when you are executing a block is that one of the warps is going to be executed, then the next warp is going to be executed, and so on and so forth. So you can say that a block contains a set of warps, and the warps contain a set of threads, right? So the only difference is the time where they are used, all right? So another nice thing about the GPUs is that we have all this huge amount of threads, but the scheduling is really, I mean, it's really lightweight. So it doesn't cost a lot to switch between threads. And one thing that is not very good is that having one thread to span many other threads poses a huge overhead in terms of their execution latency. And another property of GPUs is that we need to have synchronization barriers to be hit by all the threads so that we do not incur in deadlocks. So that's something that we need to care about. So having this, I mean, we need to be really careful in our code generation so you can really accommodate all these constraints. This is from the GPU side, but we also have some constraints about the compiler side. Because this is a new feature that we want to add into Clang, and of course we want to do that without disrupting whatever is in Clang. So, I mean, we want, whenever possible, to have all the OpenMP related features to be centralized in one block. And we want to reuse, all the code generation that is already present in Clang as much as possible. So if we want only to process our directives, and if possible, to leave the code gen of each one of the statements that are not related to the OpenMP untouched. So that's our goal. So the challenge here is to cope with these two constraints. And our approach here is to try to implement in CUDA different approaches to do this code generation, evaluate all of them, and then decide which one is going to be best, and then go ahead and implement this approach on the compiler. So this is our approach here. All right, so just a little bit of OpenMP here. So this is a typical code of a target region. So before hitting this directive, which is a target directive, I only have a host thread. And this directive says that anything that is inside this structured block has to be executed on a device, right? Then we have another directive here that is the OMP teams, and this is going to define how many teams of threads I'm going to use to execute my code. And what is a team? A team is something that maps really, really well to a block, because it means that the threads inside this team are expected to collaborate really closely. However, there is a subtle thing in a semantics, and that is that at this point, I'm supposed to only have one thread executing in each one of my teams. So that means that I'll have a CUDA block with a single thread, and I'm going to call this thread the master thread. Only when I reach this point where I have my parallel 4, I want this thread, this master thread, to spawn all these other threads. And so only when I reach this point, I'm able to take full advantage of the massive amount of threads I have in my architecture. And then after the parallel for, again, I have my sequential code, and at the end, I return to the host. Yep. So the question is if I can just coalesce these two pragmas in the same. Yeah, we can do that. So in a spec, you have also combined directives that allow you to do that. I was just doing this just for the sake of cleanness, okay? But that's true, you can do that. All right. Okay, so here I'm showing you two possible approaches to deal with this, the problems that we have in the code gen. In your left-hand side, I have what is called the CUDA dynamic parallelism, and is something that the latest versions of CUDA already provide. So here at the very bottom, I have my host function calling my target, and then I call a kernel for each one of my teams, and then inside this kernel, I'm going to call for each team all the threads I require. So this is one of the approaches in that if I'm going to write CUDA code for this, this is how this code is going to look like. In this side, so in your right-hand side, I have a different approach, which is to have a single kernel, and what I do is to spawn all the threads I'm going to require inside the target region, and then I'm going to guard some sequential regions by checking the thread ID against the master thread ID. So and in this way, I can make this region to be executed by a single thread, this region executed by much more threads, many threads you specify, and you have available in the system, and then again, my sequential part. However, and as I'm going to show you, okay, so you may be asked, okay, so what's the motivation if I have already this in place? What is the motivation for me to try to do differently? And these results here motivate that. So you can see in this, in your left-hand side, there is the results for dynamic parallelism, and I'm varying the number of blocks, the number of threads, and this is the latency of the execution. And the same thing for the scheme that has the if master something, right? So this is the if master scheme, and you can see that there is almost a order of magnitude difference in execution time. Why? Because the dynamic parallelism needs to interact with the driver in order to make this happen. So we motivate that, okay, if possible, we should have the threads already in place, and instead of spawning new threads, we should try only to manage these threads, right? However, there are still some problems with the approach of the if master, and I'm not going into much detail in here, but if you have like more complex control flow, if you have like the results being generated in parallel regions to be used in sequential regions, you may need to go to each statement in my code and adapt it to an OpenMP implementation, which will be highly disruptive of the compiler implementation. Another thing is that if I have a more complex control flow, I may have different synchronizations in different paths, and some threads are going to read that synchronization, some other threads are not going to do that. And the result is that we'll have a deadlock, and we don't want that. So the solution we came across was to use what we call a control loop scheme, and here, so this computes more or less the same thing, and I shaded in gray these two areas that are managing labels for my sequentials and parallel regions. So here, in these two places, the threads, each thread is going to understand if it is a master or not by checking its ID, and going to grab what its current label that is going to determine what is the next workload that thread is supposed to execute. So after this point, we have a switch, and based on the label, the thread is going to select, okay, I'm going to execute the sequential region, or I'm going to do the parallel region. And then this is inside a loop, and all the threads are going to wait here until the current workload is done. So I have only a single synchronization, and I'm able to make the code gen for each sequential and parallel region untouched, because I can generate each one of these cases when I process my directives, and I don't need to change anything inside each one of these cases. So I only need to change my insertion point and emit my code in each one of these cases. And the good thing is that we are able to do this, which is much more general and have more coverage of more cases. And by the way, so far we weren't able to find any code that cannot fit this model, and we can do that only with less than 5% overhead regarding the if master scheme I was showing you before. So that's very good news. I mean, I don't have. There's more details on this in a paper that we presented in LLVM for HPC workshop last Monday. So if you are interested in knowing more details, more intermediary steps in all these different approaches, you should check the paper. It has all the details for you. All right. Okay, so you may be wondering, okay, so where can I get this, right? So in this picture here, I am presenting how the OpenMP support has been developing into Clang. So in this side, we have the main repository, and what happened is that in a last stable release of LLVM, a snapshot was taken to an external repository that is in his website, and all the OpenMP implementation has been added on top of this. And at this moment, all the contributions that we currently can find here are being gradually merged into the LLVM main repository, and we expect that somewhere during next year, I mean, the two things are going to be a single one, and you have all the OpenMP implementation in a central space, in a central place. So about the offloading support, we are currently developing in this block, like the block in here, in the GitHub repository. All right, so how to use this? So I mean, it's very straightforward if you want to use it. I mean, you only need to go to this website, download the source code, compile it as you usually do, and then you only need to call Clang, say that you are interested in compiling the OpenMP directives, and specify not only the host target, which in this case is a PowerPC and with a Power 8 CPU, but also the targets you care about. You only need to provide the triple of the target you want to support for the target regions that are in your source files. So only a final thought. I mean, some acknowledgements. I mean, we have been actively working on the offloading part, but I mean, there are so many more components that are being contributed by other people. I mean, not only the code drops themselves, but also the code reviews, the way the specification, the offloading specification has been done. And I mean, some of these contributions include not only IBM, there is Intel, Texas Instruments, DOE Labs, and many other distinguished members of the LLVM community. And I guess that's it. And I'm happy to address any questions you guys may have, right? Yep. Well, I should probably say that. I mean, there are some features I presented today that are not already in there.
The GitHub URL is on this.
All right, so you guys can get it from here. Oh. Please go ahead. So we are actively working on this, and we expect by the end of this year to have at least the support for some interesting examples already in Clang and ready to use, and we are very happy for you guys to try it and give us feedback, and so we can know how to do better. All right.
How do you compare your results with respect to a native CUDA implementation of the code? So if you
all right. So the question is, how does these results that I was showing here compare? I mean, using OpenMP will compare with CUDA. Well, we currently don't have an answer for that. I mean, this will depend also on the data and how you deal with the data. I mean, I would say that in the first iterations of the compiler, you should expect to have some overhead for OpenMP, and our goal is to look into the deficiencies and try to address one of them, so the two things can start to have like closer performance closer to each other. Right, but I mean, we don't have all the flexibility in OpenMP that you currently have in CUDA. But I mean, writing an OpenMP program is much easier than writing a CUDA program, right?
What's the OpenACC support in Clang?
So the question is, what is OpenACC support in Clang, and the answer is none. So there is no, and as far as I know, there is no plans to do that. Well, actually, I should probably say this. I mean, I think that we all should work really hard to make OpenMP and OpenACC to merge into a single path. Because that before there was only OpenMP, then OpenACC diverged from OpenMP, and now you have some interesting features on OpenACC to support targets. And what we are going to try to do is to learn, from OpenACC and try to, integrate all the good things in OpenMP, and in the future we should expect to, and for the sake of all the programmers, to have only a single directive language to deal with everything. All right. So you have a question?
How come that targeting for CUDA? How come that targeting for CUDA, not OpenCL?
Say it again.
Why this system is targeting for CUDA? I mean, there's OpenCL, but why? Maybe there is a reason.
Well, I mean, my understanding is that, I mean, OpenCL. Oh, okay. So let me repeat the question so everyone can listen to it. So the question is, I mean, why bother do this if we have OpenCL, right? So that's more. So your question is why should we try to do this in OpenMP if we already have OpenCL?
Why did you target CUDA?
Oh, okay. So I'm sorry, I didn't understand. Okay, so the question is, how do we target CUDA instead of OpenCL? Well, the OpenCL programming model is very, very similar to CUDA, and we currently care about NVIDIA GPUs, and CUDA is the main and probably the programming model that will allow you to get more advantage of the GPUs. And I suspect that if you do the same evaluation of OpenCL, the kind of results that you would see will be very similar to what I showed you today.